Artificial Intelligence in Deep Brain Stimulation for Movement Disorders, a Systematic Review and Technology Readiness Assessment.
Okay, Alex, let's jump right into this paper that questions whether AI in deep brain stimulation for movement disorders is truly ready to leave the lab. The authors point out most current models rely on small, retrospective datasets and rarely get validated across different centers.
So before we imagine fully automated DBS programming, we must ask how robust these methods really are.
Exactly. And when 70% of studies come from just 3 countries using single-center data, what does that say about generalizability? Are we seeing real-world performance or just local overfitting?
It's like testing a car only on flat tracks and expecting it to handle mountain roads.
Right. Plus, most papers rely on cross-validation without proper external or temporal splits, meaning they're not truly prepared for varied conditions.
And accuracy numbers are often reported without uncertainty estimates, which is risky when decisions affect someone's quality of life.
Exactly. Then there's the ethical side, without transparency and human oversight, who takes responsibility if something goes wrong.
That raises a critical question about whether we're moving toward responsible deployment or just creating impressive but untested artifacts.
Well, if this trend continues, AI might soon drive adaptive stimulation decisions, but only after cleaning up validation and regulatory hurdles.
So what does validation look like in practice?
Think of it as friends practicing dance moves together without leaving the room, repeatedly testing within their own group to see stability.
That's K-fold cross-validation, where about 30% of studies split data into 10 groups and rotate testing. And for a stricter check, some use leave one subject out validation. Each person takes turns being the tester while others practice. So they're ensuring the system works when new people join?
But then there's the reality of small sample, high-dimensional settings. 26.4% of studies fall into this category. It's like teaching someone to paint with 1,000,000 colors, but only one brush at a time.
Without proper regularization or validation, those models latch onto noise instead of real patterns.
Right. And when it comes to measuring success, most report accuracy around 56%, with sensitivity and specificity close behind.
They also track more nuanced metrics like F1 score and precision in targeted studies, though those show up in only about 13% of cases. So the field uses different tools for different tasks rather than a one-size-fits-all approach.
And that shows how translational gaps emerge when moving from controlled experiments to messy real-world conditions.
If someone wants to replicate or build on this work, they must pay close attention not just to algorithms, but also to validation methods.
Absolutely. Understanding these gaps helps researchers identify where genuine improvements are needed before deployment. Exactly. The paper reveals most studies sit at early development stages, with few reaching TRL-7, the gold standard for clinical deployment.
That gap means we need caution. Just because something looks promising on paper doesn't guarantee it works across hospitals or diverse patient groups, I see. And what about validation? Isn't that the whole point of testing in real conditions?
The paper points out that while they tested things like objective assessments and adaptive DBS, most studies didn't actually validate their AI outside controlled environments.
So we're still missing the proof that it works consistently across different settings?
They also note that regulatory frameworks and multi-center collaborations are rare, which makes sense if you think about how complex these systems need to be.
And what about those open source models they mentioned? Aren't they supposed to help with sharing?
They are, but even then, only 20.9% of studies shared their code or data.
So transparency is a problem too.
Absolutely. Without that openness, it's hard for others to build on the work or verify results.
This feels like we're still in the early days, even though AI is everywhere these days.
It really is, because the paper shows that while there is momentum across different types of data and methods, the real-world application is still lagging behind.
So what should we focus on next?
We need to focus more on solid validation and actually deploying these systems in varied clinical settings to see how they work.
And we should push for better collaboration between researchers and clinicians so the tools move from theory to practice faster. That's the challenge with AI in medicine. Great ideas, but translating them is hard. They didn't limit themselves to one type of AI. They used machine learning, including traditional models and deep learning, as well as symbolic rule-based systems and fuzzy logic for uncertainty.
That covers a lot of ground. Why bring all those approaches together? Doesn't it get messy?
It actually helps capture the full range of ways AI could aid deep brain stimulation, showing how diverse and exploratory this field is.
And they didn't just look at studies from one country or time period. Diversity in data sets and methods mattered too.
Any details on how they chose or assessed these studies?
They followed PRISMA 2020 guidelines for systematic reviews, registered their process with Prospero to stay transparent, and kept an open mind as they reviewed the evidence.
So a structured yet flexible approach. Did they set strict inclusion rules?
They defined clear criteria, like including studies that used AI for preoperative assessment or adaptive stimulation, but also allowed room for mechanistic insights that might not fit neatly into those boxes.
That flexibility is crucial given how new this area is. Does it mean some studies were less rigorous?
No rigor remained key. They just recognized innovation can come from unexpected places early in a developing field like AI for deep brain stimulation.
So an inclusive yet disciplined lens on what counts as eligible research. How did they handle the variety of methods and outcomes?
They didn't force everything into neat categories. Instead, they tracked governance aspects, how ready each study was for deployment, and generalizability across populations.
That's a lot to juggle. Any particular challenges during selection?
Balancing depth with breadth was tough. They wanted enough detail to assess quality, but also needed to cover many studies.
Sounds familiar from other reviews. They prioritized transparency and adaptability while keeping standards.
And it wasn't about declaring winners or losers yet. It was purely descriptive at first, setting the stage for deeper analysis later.
So we're looking at a snapshot of where AI meets deep brain stimulation right now, a diverse landscape waiting to be understood.
That's why this part matters. It shows what we know and how much remains unknown.
They didn't just look at one type of study.
Nope. They cast a wide net. They searched 5 major databases: PubMed, Scopus, Embase, Web of Science, and IEEE Explore to make sure nothing important was missed.
You want all the relevant pieces before building your argument.
And they didn't just throw every keyword at the wall. They broke their search into 3 main ideas: artificial intelligence, deep brain stimulation, and movement disorders.
So those were the core themes.
Then within each theme they used controlled terms like mesh in PubMed and free-form keywords such as deep brain stimulation. It's a mix of precise catalog search and flexible brainstorming.
They looked for synonyms and related ideas.
And then combined those concepts using Boolean logic and to connect the themes or within each theme to ensure nothing slipped through.
That's methodical yet clever.
It is. They required a clear description of how AI was actually used in each study.
It wasn't enough just to say we used machine learning. The paper needed to detail the type, training method, and validation.
They wanted transparency about the model structure, training data, and validation approach, whether it was clinical trials, observational studies, or even animal models with direct human relevance.
They also set a strict rule against using reviews or abstracts that weren't full papers.
No summaries without substance. No editorials alone. Only peer-reviewed articles published between 2000 and April 2025 in English.
That's a solid boundary. Makes the whole thing more trustworthy.
And they were careful to exclude cases where AI played no real role, no analytical or decision-making function.
It wasn't enough to mention AI there, needed to be real impact.
They wanted studies that truly used AI as a tool, not just as a buzzword.
I like how they set the stage for everything else.
And honestly, this approach gives us confidence we're looking at genuine innovation rather than hype.
But what happens if you find something in one database that doesn't quite fit?
They probably used a systematic review process to evaluate and compare across sources, ensuring consistency while respecting each study's unique context.
That sounds like a lot of work.
It is, but it's the kind of groundwork that lets us trust what comes next.
Now we can look at how they evaluated the studies. They organized the data into 7 main categories: study details, movement disorder specifics, procedure stages, data types, AI methods, reliability checks, and performance scores.
And they didn't just count numbers. They captured deployment hurdles and real-world use that often get skipped in lab papers.
They also tested 3 separate ways to confirm their results weren't flukes, important when you're talking about medical tech.
That independence check is key. Trusting a device based on shaky evidence just doesn't cut it.
It's all about building confidence before anyone relies on the findings every day. Since the work covers image segmentation, signal classification, reinforcement learning, prediction models, and computational simulations, no single risk of bias tool worked for everything.
That's why they skipped PROBATIS-T and used a consistent qualitative appraisal instead, keeping nuance over a misleading overall score.
For translational maturity, they mapped to technology readiness levels from TRL 1 all the way up 9, tying each level directly to what the study actually reported.
Reviewers independently scored bias elements like sample size versus model complexity, training versus test splits, external validation, and code availability. No composite ratings, just clear notes.
Both reviewers also judged data provenance, workflow fit, and real-world deployment readiness for each entry.
The end result is a detailed map of strengths and gaps, rather than a single number that could hide important differences.
What truly matters in reporting can be unclear at times.
When you can't tell if something is at a higher maturity level, they just give it the lower TRL to be safe.
Because TRLs measure how far along the system is in moving toward regular clinical use, not necessarily its scientific quality or how well it works mechanistically. Lower TRL studies still matter. They're early steps on that path. If you would like more information, the full rubrics and examples are openly shared on Figshare.
That is all we have for today. Thank you for listening, everyone.
See you next time.